Software Engineering Radio Episode 21, Error Handling Part 2.
Welcome to a new episode of Software Engineering Radio. This is part 2 of exception handling. On the microphones are Michael
and Arno.
To start off, Arno, I think we discussed about two kind of categories of exceptional conditions. Could you explain them briefly?
Yes, well actually it's good to start by defining some terminology. Not that I'm into this formalistic stuff, but it's good to have clear terminology for the rest of the episode and to discuss exceptions or exceptional conditions. Well, this distinction is really about whether exceptions or exceptional conditions are expected or not expected by the programmer. An expected exceptional condition is something that you know about and that can occur and that someone might want to handle in a way that a caller of your code might expect, that you want them to expect and to handle maybe. For example, if the network is down in a network call, or the database is down, or someone passes in an invalid name to your code, then this may trigger an exceptional condition that you cannot handle or do not want to handle in your code, and you notify the caller and expect the caller to deal with it. There's a chance of that. Sort of you document it as part of your documentation of your class, method, or subsystem, or whatever, and then pass responsibility to the caller.
And the second category?
Well, the second category is things that are unexpected. And it's, at first glance, it's somewhat weird to even think about unexpected exceptional conditions and notifying of them. The main cause of unexpected exceptional conditions are, of course, bugs. Or just other exceptional conditions that no one thought it or thinks it is necessary to handle. Sort of, if this happens, no one can really recover from it. Just make sure nothing really bad happens, shut down the system, that sort of thing. So you sort of restrict yourself to handling expected conditions in a well-defined way, and then you have unexpected kinds of exceptions that you sort of handle in a catch-all way. That sort of makes sure nothing really bad happens, but that the expectation is not as for the system to behave as gracefully as with the expected conditions. Actually, this brings me, this stammering of mine, brings me to an underlying problem of talking about exceptional conditions, of talking about errors, of talking about problems in software, and that is, this is one of the softest topics in software engineering. Handling errors is not really well understood. There are lots of different definitions, lots of different approaches, and there are very, very few hard-defined rules how to do it well.
Our recommendation here is for your project, or what we recommend here is to separate the terminology and say exceptional conditions that are expected that you can kind of expect are called errors, and the truly unexpected exceptional conditions are then exceptions. And this is not to confuse with the Java language terminology.
Yeah, definitely. Java does not distinguish these very well, but this distinction is really quite helpful at the architectural level in thinking about how to deal with them. But, well, maybe it's easiest to sort of dig into the actual good stuff, to take a closer look at what you can categorize and how you can look at exceptions.
And that is, I believe, our model of levels of guarantee that have an impact on the design and the software architecture.
Yeah, exactly. Actually, these levels of guarantee go back to Herb Sutter. He documented them in his book Exceptional C++. And these levels of guarantee that we're about to present go along the lines of Herb Sutter. It's not exactly his categorization, but it's close to it. It's a very good book, very recommendable. Well, the first and fundamental level of guarantee is that a piece of code guarantees that whatever happens, it will be stable, it can be called again after the problem. There will be no resource leaks, whatever happens. I mean, there's lots of code out there that does not agree with this level of guarantee, but still this should be the fundamental level of guarantee that basically any code you have in production should adhere to. Let's look at these different aspects of this level of guarantee, of this fundamental level of guarantee, and think about what the problems are if they are not met. I mean, if there is an exception or if there is a problem of any kind, and there's a resource leak, for, let's say, a database handle or a GUI handle or whatever, maybe a socket, a thread, whatever, is lost. This is an operating system resource that is gone forever. Well, at least as long as the process lives, which is bad enough. So any code must ensure this, that whatever exception condition occurs, all resources are freed. There are different idioms in different programming languages, finally blocks in Java, destructors in C++. Every language has its own means, but this is really, really important. Whatever happens, no resources must be leaked. Another thing that is more subtle is that the code that was called, the piece of code that was called, must be in a stable state. Especially if, this is the point of constructors. If a constructor throws an exception, it means that the object is not initialized and it's not available. This is part of the value of constructors, that you either have a fully initialized object or no object at all. But let's say you call an initialize method sometime later on, and in the middle of the initialization something goes wrong, some sort of error condition occurs, then you might have a partially initialized object. Even if there's no resource leak, this can be a problem. If someone calls it later on, then this might cause any sort of undefined behavior. This is not part of the fundamental guarantee. The fundamental guarantee says whatever happens, the object must be stable and callable in a well-defined state, sort of. And it does not necessarily have to do something useful. It's perfectly okay at the fundamental level of guarantee if any further call just throws another exception. But it must be in a well-defined state.
So if I understood you right, what do I really do with when a constructor fails? I will have an unstable state with that object, right? So what should I do then?
Well, with a constructor, there's typically no problem, because if the constructor aborts abnormally, then the language that you use ensures that you do not get a reference to the object. Well, modern languages do it that way. So, if the constructor fails with an exception of some sort, you just do not have an object at all that you could have a pointer or a reference to. So, if the constructor fails, there's usually no problem with a non-callable object. There might be a problem with resource leaks, but there's definitely no problem with an uncallable object.
So I would have a null pointer returned or something like that?
Well, from a constructor, if the constructor throws an exception, you don't get any pointer that is returned. And languages ensure that you do not have a pointer that can be assigned to a variable. So if a constructor throws an exception, the languages ensure that you do not get a pointer or a reference, be it null or whatever, that you could dereference and use to access the object later on. This is why initializing the object in the constructor is such a good idea if you want to meet the fundamental guarantee of consistency.
Okay, so this was the first guarantee, first level of guarantee?
I'd like to add an example, sort of counter-example. From the Java world, the Hibernate persistence framework is a bad example of this. It does not adhere to this. The handle to the database is called a session, which is a complex, big object. It has a session cache, first-level cache, where you can register objects. And the Hibernate documentation says, whenever any sort of exception occurs in the session, that could be an optimistic log exception or whatever, the documentation says the session will be in an undocumented state, and you need to discard it and start with a new session. This is sort of the opposite of what the fundamental level of guarantee says. This is bad design. In Hibernate, the good idea is to do it differently. But yeah, let's go to the next level, the basic guarantee. The basic guarantee builds on the fundamental guarantee, but it also demands that the object be usable. So the basic guarantee says, yeah, there must be no resource leak, and the object must be in a well-defined state, stable state, and it must be usable. So the fundamental guarantee permits you to set a flag, there was a problem, and then have a guard in every single method that just throws an exception saying, this object is in an invalid state, it cannot be used right now, try again later, does not make sense, but use a different object. But the basic guarantee says, whatever happens if there was an exception, the object is still usable. This is typically achieved, or this guarantee is very often present if you have stateless components in your design. Because a stateless component, whatever happens, or a component with no visible state, can be called, whatever happened. Data is passed in, data is passed through, but the component is callable again and again and again and again. So there can be exceptions, yes, but any exception, any problem, any exceptional condition that occurs will not invalidate the component. It can still be used. This is why statelessness is good for robust code, and why stateless components make error handling so much easier than stateful components. The third level of guarantee is the strong guarantee. This is Herb Sutter's terminology. And the strong guarantee demands transactional semantics, rollback semantics. So if a call fails, the strong guarantee demands that the object afterwards be in the same state, the same observable state as it was before the call. The distinction between state and observable state is an object might do some internal caching that is not visible from the outside. And rollback semantics do not demand that this internal caching be undone, but any visible state from the outside that is not just for performance optimization, that must be rolled back. And rollback semantics are typically achievable. I mean, they're often desirable if you deal with state, because if you do not have rollback semantics, the caller needs to sort of cache create a copy, cache the state before he makes a call, and then do all this complicated stuff. And it's far better service of a component of code to do that inside the code that is called. So immutable objects are a design practice that is very helpful to achieve this sort of guarantee, to achieve the strong guarantee, because, I mean, if you have immutable objects, whatever happens, they cannot have changed in their state. So if you make a call and any change just results in a modified copy being returned, then obviously you have this rollback semantic because the original was not modified at all. And this is sort of the simple case. If you have single call transactions, sometimes it is desirable to have explicit sorts of transactions that span several calls with explicit commit and rollback. But once you go to that level, it becomes more and more complicated, and you start implementing your own database system. You usually don't want to do that. And especially in business systems, a typical design is that you have stateless components at a business logic layer, and then the state is inside the database. And the database provides this sort of rollback semantics, which makes it easier to implement that, sort of trivial sometimes, to implement for the components that are above the database layer.
Okay, so this was the strong guarantee, and the next one is the no-throw guarantee.
Right. I mean, the no-throw guarantee guarantees just what the name suggests. Whatever happens, you can rely on on a method call not to throw anything. This is sort of very rare. I mean, even if you have it's very rare for languages like C# or Java, because basically whatever you call could trigger an internal error of the virtual machine or an out-of-memory condition or that sort of thing that is sort of non-deterministic. So this level it's also rarely necessary or helpful if you deal with this sort of business systems doing Java or C#, but it is very important if you go down to closer to the system, to the operating system, inside the operating system, nearer to the machine. if you do embedded systems of some kind, or if you implement a database system, then it's very important that you have portions of code that you can rely on not to throw anything. But the key point is not to achieve the highest level of guarantee you can. The higher the level you achieve is the more effort you need to put in, and it wouldn't pay off. But the key point is to think about your design in terms of what guarantee does my code provide? Or, looking at it differently, what parts of my code need to provide which level of guarantee? To sum these levels of guarantee up, the key thing is that the fundamental guarantee should be provided by every single part of your system. Whatever happens, you must not have resource leaks, and whatever happens, you must not have code that is in an undefined state but still available to clients. You should avoid these. And then, building on that, you can think about providing the basic guarantee that says whatever happens, the components will remain reusable. The strong guarantee, I have rollback semantics, or the NoThrow guarantee, if you want to have portions that you can rely on, that whatever happens, they deal with it gracefully and contain any exceptional condition.
I guess it will be really hard listening to the discussion achieving a no-throw guarantee for large components of your system.
Well, yeah, it's certainly difficult, and oftentimes it's not necessary. But, then thinking of embedded systems that are mission critical, I would hope that a pacemaker that is in a heart, or that the flight control system in an airplane sort of provide a no-throw guarantee.
All right.
So, yeah, there definitely is scope for systems, even for larger components, that must contain every problematic condition. But, yeah, I agree, it is difficult to achieve, and for many systems, especially for the typical business systems, this effort just does not pay off.
So, going back to our earlier terminology, I assume that we would call that they should only deal with errors and repair things and learn how to deal with errors, and that there are basically no exceptions in any case.
That is actually a good question. First of all, it is true. The important thing is dealing with errors in this guaranteed way. Errors, just to recap, errors were expected problems. And yeah, these are the really important things. But then, depending on the situation, especially when you have mission-critical systems that provide a no-throw guarantee, it is a good idea, or there are situations where it's a good idea where it's necessary to deal even with exceptions gracefully. So yes, usually you think only about errors and dealing with errors when you design your system, and sort of shut down gracefully if there is some sort of bug or something. But then you need to think about, if there's a bug, how much reliability, what sort of behavior do I need? And sometimes it is possible and even desirable to handle these as well. Which brings us to the next thing, I think. The next issue of architectural concepts of dealing with exceptions. The single most important best practice of dealing with exceptions is to handle the exceptions at subsystem boundaries. To partition your system and only deal with exceptions at these boundaries of the system. This might be if you have a big monolithic system, then you might just have one component and deal with any sort of exception at the GUI or right below the GUI, sort of popping up a message box saying there was an internal error, I'm shutting down the application gracefully, or there was an internal error, I'm not doing anything, and let's hope and pray that the system will continue to run stably, or whatever. But it is important to not clutter your code with catch blocks that handle exceptions all over your code, because this makes this code unreadable and it clutters up the design and makes it very hard to understand what is going on, and also to sort of obliterate what is really going on there.
So this was your recommendation for exceptions. How about errors?
Well, for errors are sort of different. If an error occurs, sort of an expected problem, the expected part of the definition of error means that someone thought you might want to handle it rather locally. You might be interested in it and deal with it. So if you can, and it makes sense for you, then you should handle it contain it and handle it locally. Examples of this are connection failover. If a database is down and one component says the connection is stale, database is gone, you get an exception, a technical exception, which in our terminology would be an error. Then you might try to reconnect to the database or switch over to another database with worse quality of service characteristics or whatever. Or if the network is down, you might, in some situations, want to return data from a cache. Or if it was a call that was to store data on a server, you might sort of put this call in a queue, just acknowledge it, and try to send it later. This is a strategy, this is the architectural strategy of thinking about error conditions and how you can gracefully handle them locally. This does not mean that you always can do that. I mean, this is the failover of databases or caching calls to a server if the network is down. Yeah, there are many systems that do that, but then there are also many systems that do not do that. But, well, that sort of makes move these things from the error category into the exception category of unexpected things that you just sort of treat as a bug, that sort of thing. So this distinction is sort of not very strict. It's hard to keep up. But if things are in the error category, if they are intended to be expected, then you should deal with them locally, contain them, retry, or whatever, if possible. At least think about that in your design. One important thing is never just catch an exception, or a technical exception, be it an error or an exception. Never just catch it and hope everything goes well, which is one of the big temptations of having checked exceptions in Java, because then you are forced to deal with them in some way, and this sort of leads to this really, really bad practice of just catching and hoping that no one will notice. That is definitely a bad idea. So either if there are exceptions, they're unexpected, just let them pass through and handle them at subsystem boundaries, team boundaries, distribution boundaries. And if it is an error condition, think about dealing with it locally. And if you cannot or do not want to deal with it locally, then you can also let it go through and turn them basically into exceptions.
Okay, I guess then you have some rules of thumb for us.
Right, exactly. These rules of thumb go back to the book by Sidersleben about modern architecture. They are not exactly what is written in that book, but that book inspired these rules of thumb. The first rule of thumb is to distinguish between errors and exceptions. When you design a component, when you design a part of the system with an interface that others will call, it is good to think about what are the things that can go wrong, and which of these things would be meaningful to a caller to deal with, and which wouldn't. I mean, it's good to think about that, but this shows that the distinction is sort of hard to get exact, because you will not know which people will call your code, how that will evolve. And some things are really hard to put in one of the categories. For example, security. If you have an authorization check, it is common practice for an authorization check to throw an exception if the authorization fails. Is that an expected or an unexpected exceptional condition? You sort of expect it, that it can happen, but then it can happen everywhere. Every single call can trigger this, and you do not want to handle it locally. So the handling is sort of like, for an exception that is at a high level, you cannot really deal with it locally. So this shows that, yeah, it is good to think about this distinction, but then don't think about it too much and try to be over strict in applying this distinction. Just will not work. But the key point is to give some sort of documentation of what can go wrong in a call, what sort of exceptions, technical exceptions, signify what sort of errors. You might want to write that down in API documentation or in automated tests or in whatever way, but yeah, that should be documented in some way. Another good practice, rule of thumb, is to make your exceptions or errors self-documenting. As we said in the first episode on error handling, there are several different parties that are interested in the information about errors. First, it is users. They're easy to satisfy mostly. If something went wrong and is not an error condition that is really meaningful for them, that allows them to interact, so they sort of get something like internal error. And they're fine with that. But then you have system administrators that are working with the computers in the data center, they need specific information. And the most interested people that need the most detail are programmers. So whenever a technical sort of exception is thrown, signifying an error or an exception, it means that it should contain all data that is necessary to understand, to reconstruct the context, to reconstruct what went wrong, what led to this, and that everything that is necessary to handle this exceptional condition. Which means that oftentimes exception classes have data added to them, or you have an inheritance hierarchy that reflects the way in which they will be handled differently. The key point here is to hit the right level of detail, which is, as always, difficult. But yeah, some level of detail is necessary, is very helpful. For example, some flag saying if the server will be stable after this exceptional condition or will be unstable after the exceptional condition. That sort of thing is essential for handling. But then some people just create a huge tree of exceptions, of inheritance hierarchy of exceptions, and a very fine granularity, and then do not differentiate in the handling. This is effort that doesn't pay off. So yeah, you should make self-documenting exceptions, but don't overdo it.
And that kind of leads already to the third rule of thumb, to define exception and error classes only when necessary for the control flow. This means keep it as simple as possible, I guess.
Yeah, definitely, exactly. Yeah, that's what I was saying. Many exceptions are handled and reported in a very generic way. Oftentimes you just have a catch clause that sort of catches most exceptions, and handle just logs them and pops up a message box to the user saying there was an internal error, and notify the system administrator maybe that he should restart the server, whatever. If there's no difference in handling them, then there is no point in throwing different kinds of exceptions. Just doesn't pay off. And well, there's different cultures in different programming languages, but in many languages there is sort of a culture of aesthetically designing, putting much effort into designing nice and complete and huge exception classes. This is often just not necessary, which means it is a bad idea because it is effort that doesn't pay off. Then another rule of thumb is that technical exceptions are often not the best technical way, or anyway, they're not the only technical way of reporting an exceptional condition. Often they are, but then return values are still present. But especially collecting parameter is a great pattern for notifying of problems in an easier way, in a more handy way than exceptions are oftentimes. Collecting parameter means basically you pass a collection as a parameter to a method, and if something goes wrong inside that method, it just adds entries to this collection for everything that went wrong, which allows to report several problems, a collection of problems back to the caller, whereas an exception allows just one single problem to be reported. This is very useful, for example, for doing validation in the user interface. If you have a dialog with 24 fields, let's say, and you validate all these and have constraints on them, then badly designed systems just throw an exception in the checking code. The first check that fails throws an exception, which is returned to the user interface and prints one message. This constraint was failed. For example, the name field must not be empty. Then you fill that, click commit again, submit again, and then you get the next message. That sort of thing is bad design, but it's sort of the only kind of design you can do if you use exceptions for reporting your errors. But there it is very good practice, established practice, to pass a collection to the validation check and then have them add one entry to this collection for every validation that fails. And when all the validation checks are through, then you return the whole collection to the user interface and display a whole list of things that went wrong. So throwing exceptions is not the only way to report problems, to report exceptional conditions, and it's good to keep that in mind, especially when you design user interface.
Okay, so the last rule of thumb?
The last rule of thumb is robustness goes first. And performance tuning is a distant second, if even second, maybe third or fourth. Robustness goes first. This should be obvious. It's been said so often, but still it is not obvious. And I hear that over and over and over again. People saying, using exceptions is cost performance. It's slow. It has a huge overhead. So I will not use exceptions, but whatever. Use return codes because that's faster. Or I will create an exception, store that exception, and whenever something goes wrong, I'll just throw this pre-calculated exception. This is weird. This makes for brittle code that can break easily. It means that you get information that may not be accurate in the report of the problem. I mean, exceptional conditions are rare, or should be rare anyway. And thinking about performance in the handling of exceptional conditions is usually a really, really bad idea. Exceptional conditions are so rare that usually it does not matter if there's an overhead, and using the technical means of exceptions has become quite fast by now. Yes, it is slower than a return code, but that is just something that does not matter at all. No one should care, and if you do care about that, for example, if you're in an embedded system, then you should at least measure the impact it has. And if you have measured, and yes, exceptions are your bottleneck, the bottleneck in your design, you might want to redesign. And if all these means fail, you might consider removing exceptions or make them less robust. But simplify your design, keep it simple, and use exceptions. I mean, exceptions make for robust and simple, as a simple technical mean to keep your code, most of your code, free from the details of dealing with problems. If any other way of doing that is error-prone, it's brittle. So use exceptions and ignore performance concerns in this part, unless you want to do the effort, actually measure if throwing exceptions has the critical impact on your performance, which I seriously doubt.
Yeah, here's small experience from my side. When I did development in the C++ for an embedded system, we actually measured having the compiler include exception support code into the generated binary. Mm-hmm. And there we actually had a footprint overhead and we had a runtime overhead just by the establishing the stack and cleaning it up again for exception handling. Mm-hmm. So in C++, at least there is some overhead, but as Arno already said, measure it, whether it matters, whether it has an impact on your application performance.
Yeah, exactly. There are definitely systems, there are definitely situations where you do not want to use exceptions, especially in the embedded world. But yeah, the point is measure, and probably if you're doing business systems, the overhead will not matter for your system. Which brings me to one way of looking at exceptions that is sort of unusual, but it's very helpful to understand many of the issues of dealing with the technical means of throwing exceptions. And that is, exceptions are really, really complex. They are simpler than error handling without them, but still exceptions are a non-local go-to. And adding to that a non-local go-to to a place you do not know. And if you look at exceptions this way, it will help you to keep your design simple, to use exceptions in an idiomatic way, consistently throughout your system, to deal with this complexity. Use exceptions wisely and make your exception handling as simple as possible, because error handling is really, really complex.
Okay, this closed our episode on exception handling.
Michael, would you like to summarize this episode?
Yeah, okay. What I learned are that method calls should always release resources if they encounter any exceptional conditions. So basically adhere to the fundamental guarantee, and it is often desirable to have even a stronger guarantee of that class, of the method that I'm designing. So for example, have the basic guarantee that basically nothing went wrong and I can repeatedly call that method again, or to even have a strong or no-throw guarantee. API definitions should be explicit about which errors they throw and when. So this is a terminology, the error that we introduced here to refer to expected exceptional conditions. And Finally, Arno suggested to catch exceptions always at subsystem, team, or distribution boundaries, wherever there is a natural boundary between subsystems or components, but preferably at a coarse level, not at a fine-grained level. Thanks, Arno, for all the explanations.
Yeah, thank you, Michael.
This was another episode of Software Engineering Radio. The Software Engineering Radio team wants to thank Henning Pauli for providing the music, as well as Libsyn.com for hosting and bandwidth. For more information on the podcast, past episodes and feedback, go to se-radio.net.